Whitewater slams into a coastal intake, while far inland, a narrow engineered corridor pulls the sea across heat-shimmering desert. Every drop has to arrive clean, stable, and on demand. That's the challenge of desalination at scale. You can't simply push saltwater through sand and heat and expect reliability. Corrosion attacks expose metal, dust infiltrates joints, membranes clog if pretreatment slips, and a single alignment error can ripple into leaks, contamination, or shutdowns. This system exists to solve one problem: turn seawater into dependable fresh water when rainfall can't be trusted. To do that, three pressures collide. Operators need stable flow and water quality. Construction teams must assemble precision equipment in heat and sand. And end users, cities, industry, agriculture, depend on water that meets standards every single day. Consistency is the technical stake. The process relies on layered barriers, and if one degrades, recovery is slow and expensive. Before design even begins, teams have to confront the environment. The route crosses arid terrain defined by extreme heat, wind, and shifting ground. Summer temperatures regularly exceed safe working limits. Concrete curing, elastomers, coatings, and crews all suffer under uncontrolled exposure. You can't just draw a straight line and dig. Survey teams establish and recheck control points because dunes migrate and surface soils shift with wind, storms, and vibration. Small graded errors compound into ponding, erosion, or trapped air in pipelines. The water itself is unstable. Coastal conditions change constantly. Turbidity spikes, biological growth surges, temperature shifts, and if operators don't see those changes early, pretreatment systems get overwhelmed. Real-time monitoring of salinity, turbidity, and temperature becomes non-negotiable. Get the site wrong and failures don't arrive gently. Pipelines settle unevenly, joints shear, intakes silt up, and even a mechanically perfect plant can be forced offline. So the solution isn't a single structure, it's a machine stretched across distance. At the coast, the chain begins with intake screening to block large debris. Pretreatment follows, removing grit, oils, and suspended solids so downstream systems aren't overloaded. Fine filtration comes next, using membrane-based systems to block algae, bacteria, and microscopic particles. Only then does reverse osmosis take over. High-pressure pumps force seawater against semi-permeable membranes, allowing water molecules through while rejecting salt and contaminants. After separation, post-treatment stabilizes the product water. Minerals are reintroduced so it behaves like normal drinking water, and disinfection, using ultraviolet light or ozone, eliminates remaining pathogens. A small chlorine residual protects the distribution network. This interface is fragile. If pretreatment underperforms, membranes foul, pressure rises, pumps strain, throughput collapses. The design response is redundancy, parallel trains, isolation valves, and controlled bypasses so a single fault doesn't cascade into total failure. Before any permanent equipment is installed, crews have to build the site itself. On the coast, access roads and stabilized pads allow heavy equipment to work near salt spray. Temporary barriers create short construction windows where waves won't undo hours of work. Inland, the desert corridor demands grading, compacted haul roads, wind fencing, and traffic controls to keep sand out of trenches and instruments. Material handling becomes critical. Coated pipe, gaskets, and membrane elements degrade quickly in heat and dust. Shaded laydown areas, covered storage, and limited exposure times aren't conveniences, they're quality controls. Modularization keeps progress moving. Filtration and RO systems that arrive as skid-mounted assemblies so mechanical work can proceed while civil crews finish foundations. Anchoring everything is the next challenge. Pumps vibrate, pressure vessels cycle, pipelines push and pull as pressures change. Temperature swings add expansion and contraction forces. In loose or variable soils, a simple slab isn't enough. Uneven settlement twists flanges, misaligns shafts, and turns the weakest gasket into a failure point. Foundation strategies layer solutions. Where soils allow it, mat foundations spread loads. Where they don't, ground improvement, compaction, and geosynthetics creates a stable platform. In the worst zones, deep foundations transfer loads to competent strata. Along pipelines, anchor blocks resist thrust at bends and valve stations. Flexibility is designed in through expansion joints and flexible couplings, backed by monitoring to catch movement before damage becomes permanent. With stable bases in place, construction becomes a discipline of repetition. Inside the plant, survey setout defines exact positions. Major modules are placed and leveled. Pipe spools connect systems. Electricians pull power and control cables. Instrument technicians land sensors that will later govern the entire process. Alignment is critical. Pumps are shimmed until shafts run true. Flanges are cleaned and torqued in sequence. Minor misalignment at this stage becomes leaks and losses once pressures climb. Out on the conveyance line, where the rhythm is linear, survey the center line. String pipe, join sections, restore coatings, lower in carefully, bed and backfill in controlled layers. Install valves, air release points, and access structures. Verification is continuous. Welds are inspected, joints are tested, each segment is pressure tested before burial. Nothing advances unless the previous step is proven. The most delicate moment comes not during construction, but during activation. Before pressurization, pretreatment systems are flushed to remove debris that would otherwise destroy fine barriers. Flow is established at low pressure while operators watch turbidity and pressure drop. Only then does pressure ramp into the RO trains. High-pressure pumps increase gradually, allowing membranes and seals to seat without shock loads. Sensors dominate this phase. Differential pressure, salinity, flow, and temperature are tracked in real time. Operators pause at predefined hold points, confirming stability before proceeding. If pressure rises too quickly or salinity drifts, the system backs down. Air ingress, fouling, or damaged elements are corrected before another attempt. Acceptance isn't subjective, it's stable trends over time. When permeate quality holds and oscillations disappear, a train is cleared for continuous operation. None of this works without logistics discipline. Sensitive components, membrane modules, pumps, valves, are factory tested and delivered pre-qualified. Transport protects coatings and instruments from dust and impact. Heat limits how long materials can sit exposed, pushing teams toward just-in-time delivery. Consumables like filter media and chemicals are stockpiled to buffer against supply delays and sudden changes in seawater conditions. Quality gates prevent silent failure. Visual inspections confirm coatings, gaskets, and valve orientation. Non-destructive testing verifies weld integrity. Pipelines and vessels undergo hydrostatic testing to prove pressure boundaries. Instrument loops are calibrated before automation is trusted. Every component is tagged and traceable. Anything outside tolerance is isolated and corrected before it can contaminate the next subsystem. Integration turns assemblies into a plant. High-demand pumps require robust power and backup feeds. Utilities process water, air, drainage, communications, tie every skid to a control room with full visibility. Automation maintains pressure and flow, sequences valves, and reacts faster than human operators ever could. Redundancy is intentional. Isolation valves, bypass paths, and sectionalization allow maintenance without total shutdown. Commissioning closes the loop. Components are tested first, then subsystems, then the full chain. Intake, treatment, storage, and conveyance are linked through controlled ramp-ups that avoid demand shocks. Monitoring remains tight. Alarms trigger scripted responses, not guesswork. Gradually treated water stabilizes, enters storage, and begins feeding municipal systems and irrigation networks. Opening isn't the end. Long-term reliability depends on maintenance, membrane cleaning cycles, sensor recalibration, coating inspections, and planned upgrades as demand and conditions evolve. The system also lives within its environment. Intakes and screening minimize ecological impact. Brine discharge is diffused to avoid localized concentration. Construction noise, dust, and traffic are managed to limit disruption. In the end, the achievement isn't dramatic. It's quiet consistency. Seawater converted, stabilized, and delivered across desert heat day after day. That's what makes desalination at scale so difficult and so essential.